Great. Well, thanks very much again for the invitation. It's a real pleasure to be here and get the chance to speak with all of you. So today I'm going to be telling you about some work that I put out earlier this year on understanding mixed Hooft anomalies between electric and magnetic symmetries. And of course, if there are any questions at any point, please don't hesitate to interrupt me. So let me just start off with a few words of my adoration for anomalies. So one of the reasons I love working in this field so much is because symmetries really seem to be unrelentingly applicable to approaching both perturbative and non-perturbative physics. In particular, they can organize our degrees of freedom and heavily constrain their interactions. They can characterize different phases of our quantum field theories via the Landau paradigm. And they can also characterize exotic operators like topological defects. And a really amazing property of a global symmetry in a quantum field theory is its ability to possess a Hooft anomaly. So anomalies are these little gems of topological information, which give us some small window of insight into the non-perturbative global definition of the theory. And the reason that that's so amazing is because they really contribute to each one of these virtues of symmetries. In particular, since they're topological, this means that they have to be invariant along normalization group flows. So Hooft noted that they have to be matched between the UV and IR. So in particular, if I can calculate the anomaly in some UV description of my theory, but I'm naive about the IR, I can use the anomalies as some useful constraints on maybe the degrees of freedom or their interactions. Anomalies can also be used to characterize different phases of our theories. For example, if we have some family of quantum field theories and we can calculate the anomalies at different points, we find different anomalies, we can use those as labels on the different phases. And if we understand the anomalies well enough in the symmetries, maybe we can characterize some features of the phase transitions between them. They also encode a large amount of topological data, which can be very relevant for exotic operators in our theory, like topological defects. Of course, there's always a catch, and the problem with anomalies is that they're notoriously subtle. They can be very difficult to calculate or even to detect. For example, in the case of global anomalies, it can be difficult to even detect whether or not an anomaly is there. And in general, there's really no fully computationally efficient general procedure for calculating anomalies across all possible cases. Nevertheless, this is precisely the sort of problem we're going to be interested in here, which is this problem of trying to detect and characterize an anomaly. And the case we're going to be interested in are bosonic quantum field theories. So you should have in mind maybe some nonlinear sigma models with some scalars parameterizing some non-trivial target space X, or maybe you have some gauge theory with some non-trivial gauge group. But in either case, we're going to be interested in the symmetries of these theories, and we're going to partition the symmetries into two categories, which we call electric symmetries and magnetic symmetries. And the electric symmetries are easy. They're just the symmetries which act manifestly on the degrees of freedom of our theory, and they're associated to the geometric properties of the field space. So maybe there's something like flavor symmetry, and they rotate the degrees of freedom. In the example of a nonlinear sigma model, maybe my target space X has some isometries which preserve its metric, and then my electric symmetries are just the rotations on the degrees of freedom which preserve that metric. Okay, so that's electric symmetries. They're nice, they're geometric, they're manifest. On the other hand, we have magnetic symmetries, which are more subtle because they're topological. In particular, they're associated to some non-trivial topology of my field space. For example, if my field space has some non-trivial homotopy group pi k, I know that that gives rise to a species of topologically protected defect, which I call a soliton, maybe like a vortex or a skyrmion. And this is a codimension k+1 defect. So in general, it's going to be some extended operator supported on a codimension k+1 manifold. And so in particular, these objects, the way that they're defined is by excising some defect from my spacetime and imposing boundary conditions such that as my fields wind around this defect, they pick up some non-trivial winding number labeled by a homotopy class. So you might wonder, this winding number might look like some sort of topological charge. You might wonder if there's some associated symmetry for which that charge is the appropriate charge for the symmetry. And indeed, the appropriate technology to use are higher form symmetries. Since these objects are codimension k+1 defects, since they're in general some extended operator, we can use higher form symmetries whose charges are extended operators. So I'll say more about that in a sec, but it'll be useful to note that since the charges of this symmetry are given by pi k of x, which we assume to be some finite abelian group, or at least some discrete abelian group, the actual symmetry itself, the group algebra of the symmetry, is given by the Pontryagin dual, which is the group of abelian characters. Okay, so in summary, these are the two symmetries that we're going to be interested in, the manifest electric geometric symmetries and the topological magnetic symmetries.
So a question, so your Lagrangian is just literally a nonlinear sigma model, or you're trying to take a step back from that specific?
Nonlinear sigma model or a gauge theory, which should be the two examples you have in mind.
And the homotopy groups are like finite in yours? for the
They're at least
target, or-
discrete.
Okay, discrete.
Okay, so just a quick review of higher form symmetries. It's very often that in our quantum field theories, we have some extended, maybe p-dimensional defects. And very often we can associate some notion of a symmetry under which they're charged, which is a higher form symmetry. And the way that they're implemented are by these topological symmetry defect operators, which are some unitary operators supported on a codimension p+1 submanifold. And when I say they're topological, that means that I can deform the submanifold through spacetime without affecting anything like my correlation functions. And the way that this symmetry acts is by taking these symmetry defect operators, deforming them through space, and passing them through charges and measuring their associated charge. So in particular, the way that these unitary symmetry defect operators act on some p-dimensional defect is I take the symmetry defect operator, I link it with the defect, and then I topologically deform it, I shrink it until it intersects the defect, and what that yields is some phase which measures the charge of that defect under that symmetry. So magnetic symmetries are a really great example of higher form symmetries because their associated charges are these solitons, which are in general some codimension k+1 defects. And in particular, the way that we implement magnetic symmetry is we find some topological invariant, maybe some conserved current, which we can measure the topological charge of the defect with by evaluating its winding number around a cycle which links the defect. So we can use these topological invariants to form unitary symmetry defect operators. And then we can evaluate the topological charge by integrating them around some cycle linking the defect. Okay, so here's a nice explicit example, which is probably the simplest example, which is the case of a compact boson. So this is just a nonlinear sigma model where the target space is the circle. So we parameterize this by a scalar, which is periodically identified. And of course, we can look at the symmetries. So there's obviously the electric symmetry, which are just the isometries of the circle. This is just the U1 shift symmetry around the circle. We can explicitly write down its Noether current. The charge states are just the momentum modes. But the fact that the circle has some non-trivial topology, it has some non-trivial fundamental group, gives rise to a magnetic symmetry, which comes from the pi1, and the associated charged objects are some winding vortices, which in general are d-2 dimensional. And you can explicitly write down the Noether current to generate the symmetry defect operators, which implement the symmetry. So in the ordinary two-dimensional compact boson that we know and love, this is just the ordinary zero-form winding symmetry, and the charge states are just the winding modes. Okay, so that's a great example to keep in mind. So with those definitions out of the way, we can state the main question we're going to be interested in, which is given a bosonic quantum field theory, which has an electric and a magnetic symmetry, I would like to ask the question, when does there exist a mixed Hooft anomaly between these two different types of symmetries? And so I'll talk about the precedent for this question in a little bit, but the very surprising thing is that we're actually going to be able to answer this question, and we're going to be able to answer it in terms of the topological and geometric data of the field space and how its symmetries are implemented in the quantum field theory. Moreover, we'll actually be able to completely characterize the topological form of the anomaly by computing the d+1 dimensional bulk anomaly theory, which characterizes the anomaly by inflow. So I'll say a bit more about that in a sec, but in summary, this is the question we're going to endeavor to try to resolve. Okay, so with that destination in mind, this is our trajectory. So we'll start off by reviewing some background on Hooft anomalies, what they are, how they're characterized, and maybe some useful properties of them, which will inspire a strategy for how to study mixed anomalies of electric and magnetic symmetries. And then we'll actually dive into a systematic understanding to try to characterize where these anomalies come from and how we might derive the form of the anomaly. And finally, if we have time, we'll talk about this very interesting case where the magnetic symmetries can become categorical, where they become non-invertible and so need to be described by higher fusion categories. Okay. But if everyone's comfortable, let's just start by reviewing some facts about anomalies, what they are and how they're characterized. So there's several modern definitions of anomalies. By far, the most popular and probably the most computationally convenient is this definition of an anomaly as an obstruction to gauging. So the way that that works is if you hand me some partition function with some global symmetry G, you can always ask me, can I gauge that symmetry? And the way I would go about doing that is I would couple the partition function to some background gauge fields, and then to gauge the symmetry, I would have to integrate overall background gauge fields modulo gauge transformations. But in order for that to be a well-defined procedure, I need to actually verify that the partition function is invariant under background gauge transformations. So what I do is I perform a general background gauge transformation, and the way that the anomaly manifests is as a failure of gauge invariance. That is, we say the anomaly is non-trivial if under a background gauge transformation, my partition function picks up some anomalous phase, which can't be removed by a choice of local counterterm. So we say the anomaly has obstructed the gauging of the symmetry. It's not a well-defined procedure. Another popular characterization of the anomaly is as an obstruction to the existence of a trivially gapped symmetric phase. And this really pulls from the property of the anomaly that it has to be matched between the high and lower energy regimes of my theory. In particular, if I calculate the anomaly, the UV description of my theory, I know that the ground state can't just be, as long as the ground state preserves the symmetry, it can't just be some completely trivially gapped theory, precisely because of this property, that it needs to be able to induce a response in the presence of a background, which is characterized by the anomaly. So this is a very useful characterization of the anomaly when this procedure of coupling to a background gauge field is non-trivial. In particular, in the case of categorical symmetries, it can be confusing what it means to couple to a background gauge field and perform a background gauge transformation. So this becomes a very useful characterization of the anomaly. Now, I've added an asterisk in this version of the slides, of course, because there's been some very nice work done by people here at Chicago, which shows that there should be some major caveats in treating both of these definitions as equivalent. Okay, but so there's a third, more subtle and less well appreciated characterization of the anomaly, which is that it's some form of a higher form projective representation. And so this has been well known in many contexts for a long time. In particular, it's most well appreciated in quantum mechanical systems, in 0+1 dimensional systems, where it's realized that the anomaly manifests by the fact that I can't represent my symmetry faithfully on the Hilbert space. If I define some unitary operators, which I act on states in my Hilbert space to implement the group transformations, I can't represent the group law faithfully. I can only do so up to a projective phase, which can't be removed by a redefinition. But so this definition has really flourished in recent years with the development of higher form symmetries, where it's realized that the way that we implement symmetry transformations in higher dimensions are by these symmetry defect operators that we deform through spacetime. And there, the way the group law is implemented is by fusing our symmetry defect operators along different junctions. And it was realized that if I consider various different subtle configurations of these junctions and under different deformations, a ambiguous U1 phase can arise, which is how the anomaly manifests. So we think of the anomaly as defining some sort of higher form projective representation. Now, the reason that I've written the anomaly in this way as are extending our original symmetry G by some D-1 form U1 symmetry, which I first saw in this great paper by Tachikawa in 2017, but I'm sure it predates this, is to highlight the fact that this is precisely the same content as definition 1. That is, under some subtle definition of the implementation of my symmetry and the representation of the group law, what I should obtain is some anomalous phase, which depends on the integral of some D form, some differential form, over all of spacetime. But that's precisely the content of what definition 1 says, just in a more subtle way. And so the other reason I want to highlight this definition of the anomaly is because it's going to be actually the critical way in which we characterize the anomaly later on when we study electric and magnetic symmetries. Yeah?
In the short exact sequence, what are the two G's?
This is our original symmetry, and I'm just saying this is like the projective representation. So this is whatever you get by this extension. Yeah, thanks for the question. Okay, so, but for now, we're going to run with this first characterization of the anomaly, which is as an obstruction to gauging. And the reason we're going to do that is because it gives us a very nice classification scheme for anomalies, which is by this method of inflow and descent. So the way that this works is if I go back to this anomalous phase I pick up under a background gauge transformation, what I can do is I can stare very hard at this phase, and I can realize that I can get it by a different method. That is, I can get it by going up one dimension into some D+1 dimensional spacetime and defining some topological quantum field theory, which I call alpha, which is some invertible phase, which has precisely the opposite gauge anomalous phase under a background gauge transformation when I put it on a manifold with boundary. So the picture you should have in mind is that I have my original theory on my original spacetime manifold M, but now this exists as the boundary of some D+1 dimensional bulk Y, such that and inside of the bulk Y lives this invertible phase alpha, such that when I perform a background gauge transformation, they both produce anomalous phases, but these phases precisely cancel. So we say, what we obtain is something completely gauge invariant. So we say that this invertible phase alpha, this TQFT, has characterized or defined the anomaly. So we really think of defining the anomaly by finding this invertible phase alpha. Okay, so there's one more step we can take, which is to realize that this invertible phase alpha can be associated to some very useful topological invariant, which naturally lives in one higher dimension. And in the case of bosonic symmetries, where we don't care about any tangential structure. This is just given by an ordinary cohomology class. And so this is usually called the anomaly polynomial, and it's formed from, for example, characteristic classes formed from the background gauge field. And so we see that this gives us a nice characterization, a classification of these sorts of anomalies by ordinary cohomology. Of course, we could go beyond the bosonic regime and consider more general situations, in which case we would need whatever topological invariant characterizes our anomaly to encode all of the other data that we care about. For example, if we want to specify if our theory critically depends on the specification of some sort of tangential structure X, for example, think of if we're adding some fermions, we need to specify some spin structure, then it's been proposed that the appropriate cohomology theory, which characterizes these topological invariants, is given by cobordism. That is, invariance of bordisms of manifolds, which preserve this tangential structure X. So sort of the canonical example is the case of anomalies of fermions, which are known to be classified by the Aiden invariant, which is an invariant of spin bordism. Okay, but so we can connect this inflow picture back to this characterization of the anomaly as a projective representation, and we do so via the following. We notice that if I consider sort of projective representations, extensions of this form, they're precisely classified by the same cohomology group, which I just said classified my topological invariance, my anomaly polynomial. And indeed, it can be shown in lots of cases that this anomaly invertible TQFT alpha can precisely be interpreted as being the extension class which defines this representation. So now we have two equivalent ways of thinking about this anomaly TQFT alpha and how it characterizes the anomaly. One is that it characterizes the anomaly by inflow from some bulk, but also we can think about it as defining the extension class for some higher form projective representation. So these two equivalent ways of thinking about the anomaly are going to be useful to keep in mind. So we can go back to this concrete example of the compact boson to see explicitly how the anomaly comes about. And we do this by this procedure of coupling to background gauge fields. We use A for the electric background gauge field and B for the magnetic. And we do this procedure of performing a background gauge transformation. Indeed, we get some anomalous variation. And in this case, it's very easy to write down the invertible TQFT in one higher dimension, which cancels this anomaly by inflow. So there's lots of other examples we could do. For example, we could do P-form Maxwell theory, which is just the higher form version of the compact boson. This is the theory of free P-form abelian gauge fields. There, the electric symmetry is just shifting the P-form abelian gauge field by a flat P-form connection. And the magnetic symmetry is just a higher form version of winding symmetry, coming from the fact that we can have topologically inequivalent P-form bundles. And so we do the same procedure. We find the same form of the anomaly, precisely just because this is the higher form version of the compact boson. A more interesting example, which was analyzed by Clay and Thomas, is this case of the 4D CP1 model, where the target space is the two-sphere. Here, the electric symmetries are the SO3 rotations. And the magnetic symmetry comes from the fact that S2 has a non-trivial pi2. So in 4D, this gives rise to a magnetic symmetry, which is a one form, so that the associated charges are vortices. And here, indeed, it can be shown that there exists a mixed anomaly between these two symmetries, given by the second Stiefel-Whitney class of the SO3 connection, coupled with the Bach-Stein of the vortex connection. Okay. Another fun example to keep in mind is 5D SUN Yang-Mills. So here, the reason we work in 5 dimensions is because in 5 dimensions, we have particle-like solitons, which are given by instantons. And these come from the fact that SUN has a non-trivial pi3, or equivalently, the classifying space of SUN, which classifies gauge bundles of SUN, has a non-trivial pi4. So this gives rise to a zero-form symmetry in 5 dimensions, and the electric symmetry, and yeah, the charged states are instantons, and the associated Noether current is just the first Pointryagin class, which is instanton number. And the electric symmetry is just the Zn one-form center symmetry of the SUN gauge theory. And indeed, it can be shown that there exists a mixed anomaly between these two symmetries. So it seems that in pretty much any example you write down, where you have both an electric symmetry and a magnetic symmetry, it seems like if you look hard enough, you can find some mixed anomaly between them. So the question you could ask is this generic? Does there generically exist a mixed anomaly between an electric and magnetic symmetries when they both exist? So
just a clarifying question, all these examples at low energies are free, is that right?
I think it depends. I think that's right, yeah. At least on the Coulomb phase of 5D SUN for sure. So Saul Pace in 2023 precisely asked this question, which is, does there always exist a mixed anomaly between electric and magnetic symmetry in a nonlinear sigma model? So here we're also going to want to include gauge theories, and the only requirements we're going to make are that we require both symmetries are invertible. And for now, we'll start with the easiest cases, which is we just consider a single magnetic symmetry. So we just assume we're working with the lowest non-trivial homotopy group of the target space. Okay, so this is what we're going to try and resolve. So as a sneak peek, I'll just tell you the answer, what we're going to arrive at. We'll find that it's prudent to introduce this topological structure associated to the field space X called the Whitehead tower, which is a very nice, convenient way of organizing the homotopy data. It organizes the pi k data. And what we'll find is that if we take the electric symmetry, it has some action on my field space. What I can do is I can lift the electric symmetry up to the stage of the Whitehead tower. And what I'll find is that generically what happens is that when I perform this lift of G into the Whitehead tower, it will inevitably mix non-trivially with the vertical abelian action along the fibers. And this mix will be classified by some non-trivial extension class if it's non-trivial. And we'll find that if this extension class is non-trivial, if there's this non-trivial mixing, then indeed there's an anomaly, and it's given by this form. It's given by the pullback by the electric connection of this extension class coupled with the magnetic connection. So this is the formula we're going to try and derive. And in particular, I want to highlight that since we're starting off with just a single non-trivial homotopy group, and in particular it's the lowest non-trivial homotopy group, I just am really going to care about the first stage of the Whitehead tower for now. So when I say Whitehead tower, you should really just think of a bubble. Just think of just a single fibration over my target space. Okay, so we're going to try and derive this. We're going to go for a systematic understanding of where these anomalies come from and how they're characterized. And so I won't have time to reproduce all of the details and justifications which are in the paper, but they're very interesting. So if you're interested, please ask a question or we can talk about it afterwards. So first, it will be very useful to recall the fact that mixed anomalies have an intimate relationship with other symmetry structures in my theory, particularly with the allowed charges in my theory and the ability of my symmetry to extend or mix with some other symmetry in the theory. This was systematically analyzed in this great paper by Tachikawa in the case of a finite abelian symmetry, who asked the question of what happens to all of these different symmetry structures when I gauge this finite abelian symmetry A. So one useful thing that's going to keep in mind is that if I have some abelian symmetry A, the allowed charges of that theory are given by the Pontryagin dual by the group of abelian characters of A. And one well-known phenomenon is that if I gauge this symmetry A, in the gauge theory, I get a new symmetry, which is precisely given by this algebra of charges, and I call it the dual symmetry. The only subtlety being that it's in general a d-2 form symmetry if A is a 0 form symmetry. And of course, I can always undo this process by gauging the dual symmetry to get back the original symmetry. And the reason is because the Pontryagin dual of a Pontryagin dual just gives me back the original group. So I see that this procedure of gauging a subgroup, of gauging a finite abelian group, precisely interchanges these two symmetry structures. It interchanges the symmetry algebra with the algebra of allowed charges. So there's two other cases that are relevant for us that Tachikawa analyzed, which is first, imagine that my original symmetry mixes non-trivially with some other symmetry in my theory, some symmetry G, such that they form some non-trivial extension, non-trivial central extension, which is characterized by some extension class in group cohomology. What he found is that if I now gauge my symmetry A, indeed, in my new theory, I get my dual symmetry, but now that dual symmetry participates in a mixed anomaly with the preserved symmetry. And in particular, the mixed anomaly, it says topological class, depends on this extension class. It can be written explicitly in terms of this extension class. And so we could do the opposite case as well. We could start where our original symmetry A participates in a mixed anomaly, and then we could gauge A. And in particular, if we assume our anomaly takes on a very simple form, what we find is that in the gauge theory, of course, we get the dual symmetry, but now the dual symmetry participates in a central extension with our preserved symmetry. And moreover, in the case of this simple anomaly, the extension class is completely determined by the form of the anomaly. Okay, so in summary, we see that this procedure of gauging an abelian symmetry interchanges all of these different symmetry structures. In particular, first, it exchanges the symmetry algebra with the algebra of charges, and it also exchanges the ability for my symmetry to extend with another symmetry in the theory, with the dual symmetry having a mixed anomaly. Okay, and of course, the case of a finite abelian symmetry is a very restrictive case, But I should mention there exists this wonderful technology of the symmetry topological field theory, or SymTFT, which allows us to generalize this to pretty much any symmetry you might want in your quantum field theory. So we're,
Can you just give us a simple example of this case? Just gauging some abelian symmetry and flipping like the symmetry with the charges.
exactly, yeah. If I just have like any, so I think of like Maxwell theory before I gauge it. I introduce some gauge fields. I get the magnetic symmetry back, which is the dual magnetic symmetry, which like in the case of the, yeah. So the magnetic symmetry in free Maxwell theory can be thought of as like the dual symmetry I've obtained from gauging. So that's maybe the simplest example. Good.
Or normal fold,
Sorry?
or normal fold.
Exactly.
Yeah.
It's also a good example.
Yeah, the quantum symmetry in normal form. The quantum symmetry in normal form.
Yeah, that's what Jeff is.
Yes.
And so, for example, in ion physics, so this would be the mixed anomaly between SU3 and the Skyrmion number.
Exactly.
But what exactly is the statement? So there's an anomaly coefficient. You're saying it has to be non-zero, or you're just saying that there has to exist.
We're characterizing the topological form of the anomaly.
Uh-huh.
And then ideally there will be some physical information which allows us to identify the level as well. Yeah, I'll talk about that more when we get to this derivation of the anomaly.
So there was some kind of conjecture that you had on a previous slide. The conjecture is that there's always some kind of mixed anomaly structure
That's right.
that could be non-zero,
That
and
the anomaly is always non-trivial.
the anomaly is always non-trivial. But sorry, for the case of pounds, you're saying the coefficient of the West-Witten term cannot be zero, right? You're probably not saying that.
Yeah. So that was his proposed conjectures, but you're right that like the level of this obviously depends on trivial. And so that's going to be, so we're going to see how the level gets incorporated. It's basically going to be incorporated into the data of this extension class. So you'll have to analyze the extension class, and within that will be incorporated this idea of the level, and you would have to determine whether or not it's zero.
Okay.
But the way the existence of the anomaly is characterized by this extension class, but the precise level is absorbed, yeah, to the extension class.
Could you go back a slide to remind us what A hat has a mixed anomaly with?
Yes.
So,
So if my,
so you have so you start off, got it, okay. All right.
yeah.
Yeah,
If
you
my,
answer it for everybody, so.
right, if my abelian symmetry extends some other symmetry G,
Right.
in it's a central extension, then the anomaly is of this form.
But you're not assuming that G is abelian,
No,
only that it's a central extension of G.
exactly. I'm not assuming anything about G actually.
Yeah.
Great, good questions. Okay, so what we're going to do is we're going to take a look at this network of relationships, and we're going to come up with a strategy for how we might study the mixed anomaly between electric and magnetic symmetries. And the way that we're going to do that, so we want to study a mixed anomaly between an electric symmetry and a magnetic symmetry. And by staring at this, you might think, okay, a sort of first step, a great way to do that would be to try and understand the relationship between the electric symmetry and the magnetic charges, with the hope being that if I can find some notion of an extension between the electric symmetry and the magnetic charges, this might give some indication of the existence of an anomaly between the two symmetries. So instead of studying the two symmetries directly, I should first understand the relationship between the electric symmetry and the magnetic charges. So that's our idea. We're going to try and look for some notion of an extension between the electric symmetry data and the magnetic charges. Of course, this can't be a symmetry extension because these are two different objects, right? One is a symmetry, one is a set of charges in our theory. But what we'll mean by an extension, as we'll see, is that there will be an extension in the topological and geometric data of the field space, which characterizes these two symmetry structures. So that,
Aren't you sometimes calling things charges that are also symmetries? I mean, you called A hat charges, but A hat is a Pontryagin group.
yes, yeah, I've been sloppy about my language. So, I mean, when I say A hat is charges, I'm talking about the dual symmetry after I've gauged the theory. So it was originally the charges in the pre-gauge theory. In the gauge theory, it's a symmetry now, but I called it was originally the group describing the charges. So yeah, I'm sorry, but I should be more careful. Okay. So this gives us a plan of attack, which is first, we would like to understand the magnetic charges better and extract as much topological data as we can from them, find a nice convenience interpretation, which makes them amenable to study. Then we should implement or introduce our electric symmetry with the hope of understanding its relationship with magnetic charges. Particularly, we'd like to look for some notion of an extension. And then finally, once we understand that, we'll introduce the magnetic symmetry and see what the implications are for the magnetic symmetry, and hopefully find some way to study the anomaly. So this is all very vague right now. This is sort of a bird's eye view going forward, but we can go ahead and make it concrete. So first, we'd like to study these magnetic charges, which we call solitons. So remember that the way that they're defined is that I excise some submanifold from my spacetime, which is a codimension k+1 manifold, and I impose boundary conditions on the fields as they wind around it. And this winding has to take value in some homotopy class, some winding number, which I call Q. So the way that I actually measure that is I find some topological invariant, which I can integrate along a cycle which links the defect and which yields some non-trivial homotopy class, some winding number. But I see that this characterization of magnetic charge naturally defines a map from the set of cycles which can link my soliton into the possible set of winding numbers. But then, since I'm working as locally around the defect as I want in order to establish boundary conditions, I don't have to care about overall spacetime torsion. And so what I can do is I can use the universal coefficient theorem to realize that this map defines a cohomology class. So I see that I can naturally identify with any insertion of a solitonic charge, I can naturally identify a cohomology class whose coefficients are in the homotopy classes pi k. So this is going to be a nice quantity to associate with our solitonic charges, which is going to be useful for their characterization. So to proceed, there's going to be two pieces of topological technology that will be useful to introduce. The first is this notion of a classifying space of a group G. This is otherwise called an Eilenberg-MacLane space, or in the case of abelian groups, there can also be higher classifying spaces. If you don't think about classifying spaces as much, no need to worry. We're really only going to use two properties of them in this talk. So feel free to treat them as a black box while just keeping the two properties in mind. The first is that we can naturally define a G gauge field by specifying a map from our spacetime into the classifying space. And roughly the way that we do that is we think of the G gauge field as defining the connection on some G principal bundle over spacetime. And so we think there's some universal G gauge bundle over BG, and I can use this classifying map to pull that bundle back to a bundle over spacetime with some canonical connection, and that defines my G gauge field configuration. So that map is typically called a classifying map. So if we ever need to introduce background gauge fields, we will find it sufficient to just write down a classifying map. The second property that we're going to need is this relationship between classifying spaces and cohomology, which is in particular that if I define any classifying space, any classifying map from my spacetime into a classifying space, the homotopy class of that map naturally determines a cohomology class. In particular, in cohomology theory, this is typically how cohomology is actually defined. It's defined by homotopy classes into some classifying space. Okay, so those are the two properties of classifying spaces to keep in mind. The second piece of technology we're going to use is this notion of a Whitehead tower. So you've probably heard of this idea of a universal cover of a topological space X, which is suppose the space X has some non-trivial fundamental group. I claim that there exists another manifold, which I call the universal cover, which basically forgets the fundamental group, but preserves all higher homotopy data. And this manifold fits into a covering space vibration where the fiber is precisely given by the winding number, given by these the elements of this fundamental group. So the canonical example to keep in mind is this case of the circle. Here it has a non-trivial fundamental group. The universal cover is given by the line R, which I can wind as many times as I want over the circle. And the different levels, I think of the discrete elements of the fiber, are just given by the different winding numbers, the number of times I wind around the circle. So there exists a higher homotopy generalization of a universal cover, which is given by this Whitehead tower, which is basically a sequence of fibrations over my space X, which forget more and more homotopy data as I go up. In particular, we say the nth stage is n-connected in that it's forgotten all of the homotopy classes from n on downwards. So we say it's annihilated all of the lower homotopy data. And the fiber of each one of these fibrations is given by the n-1st classifying space of pi n. Okay, So what we're going to do with these two tools in hand is we're going to claim that there exists a nice way to characterize the magnetic charges, our solitons, via these tools. So remember that we naturally associate it to some soliton, a cohomology class whose coefficients take value in pi k. I can use the second property of the classifying spaces to represent this by classifying math into bk pi k. And now I claim there exists the following nice interpretation of magnetic charges using the Whitehead tower. So the Whitehead tower naturally exists over space-time. Particularly, remember, I'm just using really the first stage of the Whitehead tower, the lowest non-trivial stage. I can use the fact that our fields define a map from space-time into our field space, along which I can pull back this Whitehead tower so that I can work in space-time. And I claim that we can find the following interpretation, as I show in the paper, of the magnetic charges, which is, how should I interpret the boundary conditions on my defect as my fields wind around the solitonic charge? I claim the way I should think about it is those boundary conditions are telling me precisely how I should move vertically along the fiber of this Whitehead stage. But what kind of geometric object tells me that? That's precisely the job of a connection. So remember, if I'm given a bundle, a connection on that bundle tells me that as I move around the base space, how should I move vertically along the fiber? So I claim there exists this a nice way to represent a solitonic charge is that it can be represented by some connection on the pullback of this Whitehead bundle. Okay, so that's going to be a very useful way of characterizing solitonic charges, magnetic charges, as we'll see in just a second. So now that we have this nice new interpretation, we can introduce the electric symmetry G and try and understand its relationship with the magnetic charges. In particular, since we just saw that the magnetic charges naturally live in the Whitehead stage, it will be useful. What we should do to understand the relationship with the electric symmetry is lift the electric symmetry transformation up to the Whitehead stage. And so that we can always do that. We can always lift some continuous symmetry transformation of the base up to the Whitehead stage.
There's no ambiguity in doing that?
So there's not going to be a topological ambiguity. Yeah, I'll say more about that in a second. But so a nice example to keep in mind is precisely this case of the circle, which is obviously has this U1 isometry symmetry around. And when I lift this U1 isometry symmetry to the universal cover R, then this becomes extended into a group extension with the R translation along the line. And so this is a non-trivial group extension. There's no way to trivially extend lift the U1 isometry up to an isometry of the universal cover R. It needs to be extended by the vertical action along the fibers of the Whitehead tower. And so the key observation is to note that this is a generic phenomenon. Generically, it can happen that when I lift my electric symmetry up to the Whitehead stage, there's going to be some canonical way that the symmetry is extended by the vertical action along the Whitehead stage, or along the fibers of the Whitehead tower. The only subtlety is that for higher K, the fibers of the Whitehead tower are given by some higher classifying space. And so in general, we're going to need to interpret this vertical translation along the fiber as being a K-1 form symmetry. So we see that what happens when we lift our electric symmetry G up to the Whitehead stage is that generically it gets extended non-trivially by something looking like a K-1 form symmetry. And I have a natural way to formalize that, which is that these together form some K group, which I call gamma. So the observation is that this is a generic phenomenon. We should generically expect that this happens. And so the way that I characterize that extension is by extension class, which is otherwise sometimes called a Postkov class. And so this summarizes to what degree my electric symmetry is extended by the vertical action along the fibers. But so now what we can do is we can go back to our interpretation of the magnetic charges as a connection on the stage. And remember that what the connection does is it tells us how to vertically move along the fibers. But we just saw that the electric symmetry gets extended precisely by this vertical action. So this is the sort of extension structure we were looking for between the electric symmetry and the magnetic charges. We see that it's formalized by this higher group extension, which exists when I lift my electric symmetry up to the Whitehead stage. And so the way that we should interpret this, we can formalize this by taking our magnetic connection as some classifying map into a classifying space of pi k, And if we want to add some electric background gauge field, we can do so by specifying a classifying map into BG. And we should notice that since these two classifying spaces fit into this non-trivial fibration of the higher group, in general, we should only interpret them as components of a single K-group connection gamma. That is, they're topologically connected. In general, we should not treat them as completely independent. And so we see, in summary, that the ability to insert solitons into our theory and the ability to introduce a background gauge field are topologically connected operations. Okay, so this is that sort of extension structure we were looking for. So now we can introduce our magnetic symmetry again. And so before, we naively would have just assumed the magnetic symmetry is completely independent from the electric symmetry. And so if you wanted to couple the background gauge fields, we would have just done so independently for the electric and magnetic symmetries. We can couple the background gauge field G for the electric and A for the magnetic. But now we know a little bit better. We know that these two things should be connected through the following two facts. First, my electric symmetry, the ability to couple to an electric background gauge field, is connected to the magnetic charges via the fact that they participate in this unified K connection, where the other part of that connection is my ability to couple to solitonic charges. But the second fact we know is that the solitonic charges can't be independent from the magnetic connection because the magnetic connection needs to act on the solitonic charges. In that sense, if I think of my magnetic connection as being represented by some network of symmetry defect operators, remember that the way that my symmetry defect operators act on my solitonic charge is they act by linking and they act by evaluating the Pontryagin character to give me that phase, which tells me the topological winding number. Okay, so we see that we were too fast in assuming that the electric symmetry and the magnetic symmetry are disconnected, in particular when we want to couple to background gauge fields, because coupling to a background electric gauge field is tied to our ability to insert solitonic charges, and the solitonic charges are connected to the magnetic background gauge field via the fact magnetic background gauge field needs to act on the solitonic charges. Let's see, and how much time do I have left, by the way?
Maybe 20 minutes.
I see. Okay. Maybe for the sake of time, I won't go through all the details then. I want to get to the categorical part, but let me just briefly say, so we can summarize this relationship between the electric background and the magnetic charges by this extension class, this Posnikov class E, which characterizes the higher group. And so I should think, like, if I want to insert some electric background gauge field, I need to specify a classifying map into BG, but really that should be extended by this map E if I also want to include magnetic charges. And so naively, if I was just going to treat the magnetic background gauge field as being completely independent, I would just tack it onto this expression and it would not contribute at all. But now I know I need to do a little bit better because the magnetic background gauge field needs to act on these solitonic charges. It needs to act by this action of taking the symmetry defect operator, linking it with the solitonic charge, and performing this Pontryagin character evaluation to yield the phase, to yield the topological class. So this act of linking plus Pontryagin evaluation needs to somehow be appended to this characterization of the symmetry structure. And I claim that there exists a very nice way to do this at the level of classifying spaces, which is this evaluation map. So I claim that if I have some combination of classifying spaces of this form that I have on the right-hand side, of a classifying space of a symmetry with its Pontryagin dual, there exists an operation at the level of the classifying spaces, which takes that and precisely implements this procedure of linking and Pontryagin evaluation. And so I think this is a very cool map. I don't have time to go into the details of how it's constructed, but please ask me questions afterwards if you're interested. I think it's very useful. But so we see that how we should do better than treating this electric and magnetic background as independent is we need to implement this linking and Pontryagin evaluation. So we need to extend by this evaluation map. We need to extend by this procedure of linking and Pontryagin evaluation. So in summary, what we get is that the symmetry structure of our theory is characterized by some classifying map alpha, which I can associate to some cohomology class. And I see that this is a D+1 cohomology class of my electric and my magnetic symmetries, they're classifying spaces, with coefficients in U1. But I see that this precisely characterizes a projective representation. This characterizes a projective phase, which tells me some extension by U1 T-1 form symmetry of my symmetry. So what we saw before is that we should interpret this as the anomaly. We should interpret this class alpha, which characterizes our symmetry structure, as telling me what the anomaly is in my theory. This tells me the relationship between the electric and magnetic symmetries when I want to couple to background gauge fields. But so given some properties of the evaluation map, we can explicitly write down the topological class of this anomaly in terms of background gauge fields for electric and magnetic symmetries. So if I couple to an electric background G and a magnetic background A, I can use some properties of the evaluation map to explicitly write these in a compact formula for the anomaly. And we find that the anomalous phase is precisely, or the anomaly TQFT is precisely given by this formula that I claimed before. So this is a nice claim, but what we should do is we should take this, actually test drive it on some examples and see that it reproduces what we expect. So we can do that for the case of the compact boson. Remember that we had our electric U1 translation symmetry around the circle and the D-2 form winding symmetry. The way that we should implement this procedure is we should lift our electric symmetry up to the Whitehead stage and then find out what the extension is. And indeed, we see the extension is by the integers z, and the extension class is given by some something analogous to the Chern class, or it is the Chern class. And so if we plug this into the anomaly formula that we just had, we reproduce precisely the same anomaly that we had derived previously by other methods. A less trivial example is the case of the 4D CP1 model, where the target space was the two sphere, and we found that the electric symmetry was the SO3 symmetry, the magnetic symmetry was this vortex symmetry coming from the pi2. So we can couple, so we can do this procedure of lifting the electric symmetry up to the first Whitehead stage. The first non-trivial Whitehead stage of S2 is just the Hooft vibration, so that the universal space is SU2. And we see that, of course, SO3 lifts to SU2 translations around the 3 sphere. And this is represented by a non-trivial group extension whose extension class is the Bokstein, the second Stiefel-Whitney class. And so plugging this in to our anomaly formula, we find precisely the same anomaly that we had earlier. Okay, so you can apply this formula for pretty much every example you can come up with. And so in the paper, we go through a whole list of examples of mixed anomalies which are known between electric and magnetic symmetries, and it reproduces the exact anomaly in every case. And in fact, we do some examples where, to our knowledge, there was no known mixed anomaly before. Okay, so there's one more interesting addition to the story, which is so far we assumed that our electric symmetry was connected, but in general, that might not be the case. Our field space might have some non-trivial mapping class group. For example, if it was the torus, it could be SL2Z. And it's known that there exists a natural action of the mapping class group on the homotopy groups, which is characterized by this group called the Torelli group. So if this action is non-trivial, I need to include it. And it turns out the way that it contributes to the anomaly is if I have this non-trivial action of the mapping class group on the homotopy group, the way that it contributes to the anomaly is to twist the anomaly so that I now need to use a twisted cup product instead of an ordinary cup product. Okay. Are there any questions at this point? Right. So that's it for the lowest magnetic symmetry. We're only dealing with a single magnetic symmetry, but we can talk about this very interesting case where we have multiple different species of solitons in our theory. In particular, if our field space has multiple different non-trivial homotopy groups in a high enough dimension, we see that we get multiple different species of soliton existing simultaneously. And a generic phenomenon for what happens in that case is that the magnetic symmetry becomes non-invertible. It becomes categorical. And so this was understood in this great paper by Pace and Beaudry and Wen and collaborators, where they realized that the way to organize this data was to use precisely the dual structure of the Whitehead tower, which is the Bosonic tower, which basically organizes the homotopy data by keeping only the lowest homotopy data and then building back up, adding more and more. And so this characterizes how the different homotopy groups fit together into fibrations. And in particular, if these fibrations are non-trivial, it's telling me that these different homotopy groups can mix with some non-trivial extension class. And generically, what happens in a non-trivial topological space is that there are extensions between these different homotopy groups. And what the implication for that is that my magnetic charges themselves now need to be described by a higher group. And so the implication for the actual symmetry is that my magnetic symmetry now has to be the representation of some higher group, and that's in general given by a non-trivial higher fusion category. So there are a couple quick, nice examples where this is the case. We can go back to this case of the CP1 model. In 4 dimensions, we have 2 species of soliton. from the pi2 of S2, we have these vortices, which are charged under one-form symmetry. But S2 also has a pi3, under which we get these particle-like solitons, which we call Hopfions because of the Hopf vibration. And so we have these particles and these vortices. And so we can explicitly write down the topological currents, which compute their winding number using this nice parameterization of CP1 as SU2 mod U1. So we think of two complex scalars with some diagonal U1 gauge redundancy between them, for which we add some associated dynamical gauge field. And then, so we can explicitly compute, we can write down the pi2 current, which measures the pi2 winding number, which is just the field strength of the gauge field. And then the pi3 current is given by the Hopf invariant, which just looks like a Chern-Simons term. And so what we do is we can take these topological invariants, these currents, and form our symmetry defect operators with them. And so these compute the topological winding numbers of our different solitons, but we see that there's a problem with the one associated to the pi3, which is that it's not gauge invariant, right? It's formed from a Chern-Simons theory, so it's not in general going to be gauge invariant. It's sick. And so this manifests in all sorts of ways. One of them is that the vortices have some, in general, can have some Hopfion charge. And so the fact that this is not gauge invariant results in the fact that the Hopfion number of the vortices doesn't seem to be, it seems to be ambiguous. Okay, but the solution to this, which Chen and Tanizaki realized, which is that the real current for the pi3 winding number is not given by the Hopf current, it's given by something similar where I stack with a fractional quantum Hall effect phase. And so the resulting symmetry defect operator is actually non-invertible. It's categorical. And so this symmetry defect operator has the miraculous property that it can actually compute the pi3 winding numbers of both the Hopfions and the vortices. The only problem is that it's categorical. It's non-trivial. One more example I'd like to highlight is that in my recent paper, I found that this is also the case in the Coulomb phase of 5T SU2 Yang-Mills when I spontaneously break the symmetry, the gauge symmetry down to U1, because in the Coulomb phase, we have two species of solitons. We have instantons, but then we also have these Hooft Polyakov monopole strings in 5 dimensions. And so the fact that we have these two solitons existing in the same theory also manifests in the existence of a non-invertible symmetry. And in this case, it comes from the fact that when the monopole strings can wrap some spatial circle, they can pick up some sort of fractional version of instanton charge. And in general, that's going to be detectable by this non-invertible symmetry defect operator. And in particular, I also found that this story could be reproduced by looking at the case of the of maximal supersymmetry, because there we have a nice UV completion for the 5D n equals 2 theory. It comes from the dimensional reduction of the 6D2-0 theory on a circle. And the reason that's a nice case is because the instantons there have this nice interpretation as Kaluza-Klein modes coming from the reduction on the circle. And so you can actually see that this non-invertible symmetry has to be there by starting from the 7-dimensional anomaly topological field theory associated to the 6D2-0 theory and dimensionally reducing it on the circle. Okay. Let's see. And so just a brief comment on how our previous anomaly analysis extends. In summary, it doesn't quite work, mostly because in order to fully implement our analysis, we would need some notion of a classifying space for these non-invertible higher fusion categories for which the full mathematical knowledge is not currently known. But we can obtain a partial answer in that we can detect a non-trivial anomaly by decomposing the cohomology classes in this Whitehead tower fibration using an Atiyah-Hertzsprung spectral sequence. So if we find non-trivial homotopy or non-trivial cohomology classes, that indicates the presence of the anomaly, but it doesn't necessarily completely characterize it. Okay, so I'll just wrap up. In summary, what we've done is we've correctly detected and characterized the mixed anomaly between the electric and magnetic symmetry. And we found that the condition for that to happen is that we lift the electric symmetry from the field space up to the Whitehead tower. If it participates in a non-trivial extension with a vertical action along the fibers, then our anomaly can be written down explicitly in terms of the extension class. We also found that the mapping class group contributes a twist to the anomaly. And in the case of higher homotopy, we weren't able to completely characterize the anomaly, but we can detect it. So some interesting future questions would be to, of course, try and find the proper topological categorical technology to do the higher homotopy case. It would also be interesting to do the case of including fermions, so not just bosonic quantum field theories. And it would also be interesting to understand how we add in topological terms like Weston-Witten terms or a topological order, how that contributes to the anomaly as well. But so I'll end there.
Sorry, so how is your construction related to the Affiliation hierarchy group?
The whose higher group construction? Kapustin's? Sorry, which construction do you mean?
Like, I saw like in one of these papers, he talks about like symmetries as forming a higher group, and the Hooft anomaly is some bosonic class.
So in general, if I'm looking at like, do you mean like the symmetry TFT characterization of a higher group where I have some like anomaly term, but part of it is gauged and that forms a higher group?
Was a paper in July, I think.
Maybe you can show me. I don't know if I recall.
Okay.
You mentioned that there were some examples that you thought you were the first to computer. Could you tell us about one of them?
Yeah, so the case of the SO3 gauge theory, there is a example where you have this mixed anomaly between the the second cohomology class of SO3, which is given by W2. This characterizes a mixed anomaly between the pi1 of SO3 and between the SO3 times SO3 electric symmetry. In the paper, I think we compute this mixed anomaly.
This is for a sigma model with target space.
Yes.
SO3.
Yeah.
And I guess a general question I might have is, does this kind of mixed anomaly always have some interpretation in terms of statistics, mutual statistics of the charged object?
That's a really great question. Yeah, that's something I'm very interested in. General is so yeah, you're referring to like the Weston-Witten term, the chiral Lagrangian is like
That's an example, and then the other examples that you listed fit that pattern, but I don't know if it's a general.
That's right. So I think that's not something I have a concrete answer to, but I think it is in general a phenomenon where if I include some topological term manifestly in my action, it will affect the statistics of my solitons. And the resolution to that is sort of summarized in this great paper by Poshen, which looks at non-invertible symmetries in sigma models, where he shows that the way that coupling to some topological terms, some extra topological order, that can actually be evaluated on the soliton using like a cap product. And so that becomes, so that sort of grading of the residual defect coming from the cap product is basically equivalent
So
to.
in general, when you have an anomaly that's A times B, basically you expect that it's about the braiding of something related to A with something related to B.
That's right, yeah.
More questions?
Why was the Whitehead Tower invented by mathematicians? What do they do with it? I guess I'm just sort of curious whether it's a construction that you would sort of be led to by the physics, or it was a construction that you knew about and realized it could be adapted to analyze anomalies, or?
I mean, I think it has a ton of different applications. Like the Whitehead Tower shows up in all sorts of areas in physics, right? Like the spin extension of SON is like the next stage in the Whitehead Tower. But then above that, you have the string group, right? That's the next level up in the Whitehead Tower. And that naturally shows up in like the anomaly cancellation on the world sheets of strings, right? So there's the obvious answer, which is just, it's a very elegant way of organizing the different homotopy groups and how they fit together. But it does also seem, the different stages seem to have some physical interpretations in different contexts, but yeah, I think it has all sorts of applications. I'm not sure what the
Which came first, Whitehead or Bosonic?
That's great.
Because once you invent one, you might try to dualize it.
Exactly, yeah.
Yeah.
I assume Whitehead was first because the universal cover has definitely been known for such a long time. People probably thought, hey, some generalization.
If there are no further questions, let's thank Aiden again.